let's do a couple of examples now. First, let's try and find the total mechanical energy of a hydrogen atom. So let's remember our hydrogen atom is just an electron flying around a proton. We know that the speed is 2188 kilometers per second. We know that the distance between the electron and the proton is 52.9 picometers, where a picometer means times 10 to the minus 12. Okay, so what we mean by total mechanical energy is the kinetic energy plus the potential energy. E equals kinetic plus potential, and we mean electric potential energy. Here's where you have to think kind of carefully. Our hydrogen atom has two charges, an electron and a proton. To get our total kinetic energy, we need the kinetic energy of the proton plus our kinetic energy of the electron. All right, then we're adding on our electric potential energy. Let's use the expression we just came up with. K times charge 1, that's the electron, times charge 2, that's the proton, divided by the distance between them, our distance between the electron and the proton. Okay, right off the bat, now I insisted we had to include the proton because it's part of our atom. Compared to the electron, the proton barely moves at all. And that proton more or less stays put. So the total kinetic energy due to the proton is about equal to 0 because the velocity of the proton is about equal to 0. So we've simplified a little bit. Now let's put in our numbers for the electron kinetic energy. 1/2 times 9.11 times 10 to the minus 31 kilograms times the speed of the electron. Let's make sure we get that in meters per second. 2188 times 10 to the 3 meters per second. Don't forget to square it. Plus, K is 8.99 times 10 to the 9 newtons meters squared over coulombs squared, times my charge of an electron. Remember, you've got to include the signs for potential energy. Times my charge on a proton. That one is positive. Divided by the distance between them squared. All in all, that gives us a total mechanical energy of minus 2.17 times 10 to the minus 18 joules. It's okay for our total mechanical energy to be negative, although it's probably a good idea to stop and think, what does it mean that it's negative? What it means is you would in fact have to do work to our hydrogen atom to split it apart. It means it wants to stay together, so it's probably good that it's a negative energy. Okay, let's do another example. So in this new example, we have a proton. And here we're going to take a lot of things away from the wording of the problem. A proton is fired from very far away. A distance that's very far away is about infinity. Okay. At a 1 millimeter diameter glass sphere, so this is our glass sphere. Distance from here to here is 1 millimeter. That's the diameter. That has been charged to 100 nanocoulombs. We've got that in our diagram. What initial speed do we have to give the proton? So that's going to be moving, V initial. What initial speed does this proton have to have in order for it to just reach the surface of the sphere? So we're going to shoot it from very far away, and it's just going to get to the surface. So this picture represents where we are at the start of our problem. Call this our initial situation. At the end, our proton has just reached the surface of the glass sphere. So this is going to be the end of our problem. We'll call this the final. We know that we'd like to apply conservation of mechanical energy. So E final equals E initial plus any work done by non-conservative forces. That bit's going to be 0. We don't have any friction or anything. So our next line in our expression is going to be our final kinetic energy plus our final electric potential energy equals our initial kinetic energy plus our initial electric potential energy. Here we might pause and ask, could we solve this problem with kinematics? I'm going to say no to that one. That would be very complicated. If you wanted to calculate the acceleration, you would have to think about the electric force, and you do know that equation. It's kq1 q2 over r squared, but the force depends on the distance between them squared. The force changes as we get closer. If the force changes, it means the acceleration changes, and if acceleration changes, you can't do your simple kinematics analysis. So we got to use energy for this one. Okay, so this is K initial and UE initial. So my K initial will be the initial potential energy of my proton, 1/2 times the mass of the proton times V initial squared, plus 1/2 times the mass of the glass sphere times V initial of the glass sphere squared. That bit is 0. That glass sphere is stationary. Our initial electric potential energy, UE initial, is K times Q of the proton times Q of the glass divided by the initial distance between them. Okay, let's go back to what we thought about here a little while ago. They have an initial distance between them that is very big. It's very far away. So if our R initial is very large, if it's approaching infinity, that means our initial electric potential energy is about equal to 0. Okay, so there's our initial setup. Let's look at what we have in the final. So when our proton just touches that sphere. So our final kinetic energy is 1/2 times the mass of the proton times V final squared, plus 1/2 times the mass of the glass times V final of the glass squared. Okay, let's think about these numbers. Well, first off, it says that the proton just touches. It just reaches. If it just reaches, it means it comes to a stop as it gets there. So the final velocity of the proton is equal to 0 because it just reaches. That's what that term means. And then our glass sphere, that's still not moving. So this one is also 0. So our total final kinetic energy is equal to 0. What about our final electric potential energy? UE final. Well, that's K times the charge of the proton times the charge of the glass sphere divided by the distance between them, RF. So let's make sure we understand what that RF means. The proton gets to the glass sphere. The distance between their centers is from here to here. So this is our RF. A proton is very, very tiny. So our RF is about equal to the radius of the sphere. And the sphere had a diameter of 1 millimeter, so the radius would be 1/2 of that, 0.5 millimeters. Okay, so RF means the distance between the centers. All right, let's take every single term we just cooked up and let's put it in and see if we can come up with our answer. So we'll start by writing down our equation again. Kf plus UEF equals Ki plus UEI. All right, our initial or our final kinetic energy, that was 0. And our initial electric potential energy, that was 0. So a little bit of simplifying right off the bat. Our final electric potential energy was K times Q of the proton times Q of the glass sphere divided by our final distance. And that's going to be equal to our initial kinetic energy, which is 1/2 times the mass of the proton times V initial squared. Let's rearrange this and solve for V initial. V initial squared is going to be 2 times K times Q of the proton times Q of the glass divided by our final, then we have to divide by the mass of the proton, and then to get our V initial, we've got to take the square root. I don't think I'm going to write in all those numbers right there. K is equal to 8.99 times 10 to the 9 newtons meters squared over coulombs squared. Q of the proton is positive of the fundamental charge, 1.6 times 10 to the minus 19 coulombs. Q of the glass sphere, that was given as 100 nanocoulombs. Mass of a proton, 1.67 times 10 to the minus 27 kilograms. And our final distance was about the radius of the sphere, 0.50 times 10 to the minus 3 meters. Put all that through the calculator, and we should get a speed of 1.86 times 10 to the 7 meters per second. It's pretty fast, but it's still smaller than the speed of light, so we're okay with that number. The next question is a homework problem, so I'll leave that to work on for you, and I will post those answers.